So in continuation with the different techniques, we will go ahead with isolation. So as the name suggests, isolation is you have to separate them out. They shouldn't be together. Therefore, the channels should only be inverted beneath transistor gates. Ideally, there is a channel in between, and on either side you have the source and the drain terminal, and they should be isolated before the channel is being created. Once the channel is created, the isolation will no more exist. So, channel is created beneath the gate. The source and the drain diffusions of unrelated transistors should not interfere. That is what I am telling. The source and the drain diffusions of two different transistors shouldn't be having any interference between them. And the transistor gate consists of thin oxide and the mass sandwich formed by the wire thick oxide, and the substrate behaves as an unwanted parasitic transistor. So in case if any of the transistor and the wire try to form a transistor effect in the MOS layer, they behave as an unwanted parasitic transistor. So these field devices can be used for IO protection, and the source and the drain of the transistors form reverse biased PN junctions with the substrate or well, isolating them from their neighbors. This is nothing but the source and the drain terminal, and this is how they will be isolated. Next we have the gate oxide. So oxide which is below the gate is called as the gate oxide. The next step in the process is to form a gate oxide, and which is normally called as silicon dioxide. This is also called as gate stack, and this being able to use a thicker oxide improves the robustness of the process. So rather than using the thin oxide, according to the author, he says that thick oxide can be used. So when we consider the 65 nanometer technology used for fabrication, the effective thickness of the thin gate oxide, what I said earlier was 0.1 micrometer, now has been changed in 65 nanometer as 10.5 to 15 angstrom units. So that is the thickness of the gate oxide, which is a very thin layer. Next, gate and source or drain formations. That is how we are able to get the three terminals. Undoped polysilicon has high resistivity. That is, polysilicon normally offers resistance. So what is the reason for the polysilicon to exhibit this resistance? So the reason for the polysilicon to exhibit this resistance is because of the polysilicon material itself. So however, this resistivity can be brought down by adding the necessary dopants. By adding the necessary dopants, and the polysilicon gate sometimes acts as a mask for the diffusion to happen. So that region avoids the diffusion to be placed under the gate structure, and on either side only it is possible for the diffusion to have the dopings. This process by itself, it's a blessing in disguise. For by itself, this is called as, by itself it is providing the masking, therefore it is called as self-aligned polysilicon gate process. And if the gate was misaligned, if the gate was here and there, then we will completely not be able to do the right type of diffusion, and the transistor may not turn on itself. So gate and drain and source terminals should be cautiously be created. So how is self-aligned process going to happen? As we have discussed in the fabrication model. So initially grow the gate oxide wherever transistors are required to protect the bottom layers. Then deposit the polysilicon. After depositing, pattern is nothing but you have to have the right dimension, and in case if it is extra, that will be deleted or that will be etched. If it is not extra, you will have to scrape it or put add on to it, and that is how it will be taken care. Etching exposed gate oxide. In case the gate oxide is deposited in high quantity, it should be etched out. So the chip has windows down to the well or substrate wherever, whatever or wherever a source or a drain diffusion. So whenever you want to create a source or a drain, a window should be created. implant PMOS, NMOS, source or drain regions. Whatever it is, if you want N type or P type, subsequently you have to update it with N type or P type diffusion. And finally, implant PMOS and NMOS, source, drain regions. So once these things are ready, you will get the terminals. Terminals has to be used. So we have something called as LDD structure. So LDD structure, which reduces the electric field at the drain junction. Normally drain is where we take the output, and normally there is some electric field associated with the drain. So you have to do this lightly doped drain structure. This has to be created. So this has to be created at the drain junction, which takes care in the further processing of the IC. Next, finally, we are arriving at contacts and metallization. So almost the entire process is ready, and we need to pull out the leads in order to create the terminals. So contact cuts are made at source, drain and gate. In some process, material used, normally aluminium is used. Though copper is the best conductor, copper is heavy, so it is replaced by aluminium. But in recent trends, we have tungsten being used. So the metal is the process of building wires to connect the devices, metallization. So metal used here is the tungsten. Conventional metallization uses aluminium. As I already told you, aluminium is normally used for the only reason that it exhibits all the properties of copper, except it is light, and therefore shrinking of size is there. Therefore light device we want, that is why aluminium is used. Aluminium can be deposited either by evaporation or sputtering. So the metallization is done by these two processes, evaporation or sputtering. So what exactly you mean by evaporation? What exactly you mean by sputtering? Aluminium is deposited by this process. So evaporation is performed by passing a high electric current through a thick aluminium wire in a vacuum chamber. So hitting a aluminium wire at a very high temperature in a vacuum chamber, in a closed container which has vacuum, no air. Then it is possible to call this as evaporation. So this is the procedure of metal being converted into vapor, and that vapor gets deposited. Next is sputtering. This is done by generating a gas plasma by ionizing an inert gas using the RF or DC electric field. So using the field, you have to generate gas plasma and ionize an inert gas. Next, either you have to go for wet or dry etching, which is removing the unwanted metal. So etching, you can use wet etching where you will be using necessary solvents. Dry etching, you can just use it with gas. So this is the procedure of wet or dry etching. Plasma etching is a dry etch process with fluorine or chlorine gas. So plasma etching is nothing but dry etching, where, as I told you, dry etching is with gases, and that is how extra metal is removed. Finally, intermetal vias and metallization are applied. So in intermetal vias, so one metal to another metal you need to have connection, that is possible by vias, and metallization is applied. So polysilicon over diffusion forms a transistor, we know that. So in that case, a sharp metal wire is necessary to connect the diffusion output. So normally whenever we are using transistors or we are considering them as input or output, it is the short wires, or we normally call it as done by metal 1. Metal 1 is used for this purposes, and local interconnect is used to connect the NMOS and PMOS transistors without rising up to metal 1. As I told you, short wire in the sense, not only short, it is also thin comparatively. The thickness of metal 1 is thin than the second metal, metal 2. So they are used for input and output. Next, we have passivation. So the final processing step is to add a protective layer called passivation or overglass that prevents the ingress of contaminants. As I told you, your IC is almost ready, the fabrication procedure is over. You have to protect the whole of the structure. not only the bottom structure, the whole of the structure, and this is happening with the help of a glass layer. So openings in the passivation layer called over gas cuts allow connection to IO pads and test probe. So not only after doing this, there should also be a provision for the leads to be pulled out, so that you want to test the IC. Therefore, you have to appropriately provide uh, uh, holes rather than, okay, holes to pull out the leads and help us to do the testing. Finally, after passivation, the next step is called as bumping. So what exactly is bumping? It allows the chip to be directly connected to the circuit board. So now this helps us to have a bumping is nothing but the leads, or in an IC you have pins. So that helps us to connect to the circuit board, and that has to be provided. Last, after passivation, okay, your IC is almost ready. The next process is called as metrology. So metrology is the science of measuring. You have to measure. Metrology is nothing but study of metrics. So in semiconductor process, it has to be measured to give feedback. In normally in any of the semiconductor process, in any manufacturing industry, you have to have a feedback. So once the feedback is pakka, it is fine, you can accept the design. If any modifications that need to be changed, it is based on the feedbacks. So feedback is very important. And this is possible. This ranges from simple optical measurements of line widths to advanced techniques to measure thin films and defects such as voids. So line widths and thin films help us to have, you need to measure them. So how will you measure? Is the polysilicon right or wrong? This is our polysilicon or metal or diffusion by comparing the width. Similarly, in case of defects such as voids, in case if anything is open and you have not yet done the metal connection, so that also has to be seen, optical measurements. How much is the measurement amount of metal deposition? Okay, that is how you have to measure. Next we have optical microscopes. So they serve as a large structure and helps us to find out the defects. Next you have scanning electron microscopy, SEM, which is used to observe very small features. Next we have EDS, energy dispersive spectroscopy, which bombards a circuit with electrons causing X-ray emission. So these are all microscopic dimensions to be measured. Therefore it is normally bombardment of electrons or electron gun being projected, and that is taken care, so that has to be measured. Similarly, we have TEM, transmission electron microscope. This observes the results of passing electrons through a sample.